Okay, final exercise, which I will not be typing because it's just proving, I think. So I have the GIMP program here to write shit down. Should be nice. Okay. Consider the following function, which inserts a value into a specific position in the list. Insert at. Takes an integer, an element, a list of A's, and then produces another list of A's. Okay. It's interesting to note that the first place is identified as 0, not as 1. Sometimes that happens, which means the n will end up between the A and D. And it does. Right, insert at gives an error if the position is larger than the length of the list. When is this error raised? Question mark. Which of the following expressions results in an error being shown on the screen when executed in GHCI? Insert. Okay, though the first one obviously not, because the insert is a recursive function, but so is take 5, which means that as this one is being inserted, as soon as this function here has moved up 5 places, the program will terminate. So this won't throw any errors. This one will, because this one throws an error as soon as it reaches like 8 or something. 0, 1, 2, 3, 4, 5, 6, 7. Alright, 7. Well, 7 should still work, but 8 shouldn't work. So as soon as this is 8, it crashes, which wasn't a problem here because it never was evaluated, but because the length wants to read the entire list, it will get evaluated and therefore crash. So the answer is B. Let's write that down. 5A. 5A. B. There we go. Let's look at the other ones, just for the heck of it. Insert at 8x example. So we already established that this would crash as soon as it's evaluated. And this wants to put it at 7, which is the last place. But after that, it will still evaluate this one, right? Because it still wants to put it at the 8th location. But it won't update the list or anything, right? So this 8 will still want to be put, still wants to go here. Even though that this it will insert it after the E, this 8 won't like suddenly know that an element was inserted in front of it. So this should also crash, which is interesting, because this suggests that there's only one, right? Interesting. Fair enough. And D is fine, because this one doesn't crash, and if you then apply this one, doesn't crash either. Right, answers 2 and 3. Yep. It's a bit of a mistake then. Implement the function delete at such that. Okay. I expected I didn't need to write anything down. I didn't have to implement anything, but I guess we can still just boot up a function or a text editor and implement it anyway. Let's write this. Let's write this into like temp.hs. All right. Delete at. We'll take an integer and a list, and we'll produce another list. Easy. There's 2 ways of doing this. If you just looked at the exercise, that was the one where it splits at, which to me is, especially when you consider this implementation, because this could also be implemented as split at. But for some reason they decided not to implement this as split at, so I figured we shouldn't implement this as split at either. So if we reach 0, then we should of course pattern match on the head of the list, which we want to remove, and then the rest of the list, and then just return that. And then, oh, that's not good. Delete. This, we should have the case for, you know, when we have a problem, which is actually should be here, because if you put it here, then there is a chance that you give it the empty list n0, in which case it will try and take the head of the empty list, which doesn't exist. So you should put it here instead. What did it say? Set list too short. Let's use the same. And then we still have the one for the we can actually, no, we can copy this, replace this by an x, replace this by an I, and then we just say x and delete at I excess. There we go. Oh, I minus 1, of course. Yeah, I would say let's look at the solution, but it's way different, right? Well, at least the type is the same. Yeah. Right. Let's kill this program again. Next. Prove by induction that for all x1, x2, xs, I1 smaller than I2 smaller than length of xs, it holds that the insert of x2 and I2 and is the same as right. So of course this wouldn't be true if this doesn't hold, because then we would throw the error. But it says here both are smaller than the length, and in fact I is also smaller. That's needed because of this +1 thing. Alright. Okay. So the first thing I notice is that there's 3 options to do induction on, right? x1 and x2 are not, you can't do induction on those because you don't know the domain. But I1, I2 and length xs all have a domain of the natural numbers. So you can do it either on I1, I2 or the length of xs. I'm thinking we do it at, we use I1. Trying to think why I2 might be a problem. Intuition tells me to use I1. I mean, this would be 1, which is a little bit annoying, I guess. Yeah, I feel like that might be the best reason we have to use I1 instead of I2. So if you have 1 here, then it's easier to say anything about it, right? If you have 0 here, which we will have in the base case, then you can just say that it's x1 followed by this, which is easier than having to take one element off first. Yeah, and then this would be x1 followed by this, and then this would be yeah. Let's use it. Let's do induction on I1. So B we did. C. Right, let's start with the base case. Base case is I1 is 0. Alright. Oh, whoops, wrong. So to prove, I don't know how much of this you need to write down, but we might as well insert at, I'm gonna call it IA from now on, just to write less, of 0 of x1 into the, let's use IA here. What did it say again? I2 x2 I2 x2 into xs, and we have to prove that this is the same as this this one. Okay, so yeah, I mean the first thing we can rewrite is the 0 one, because the insert at had a this one, so we can use this rule, rewrite it to the right hand side. So then we get x1 colon, then the IA of I2 x2. Oh, then we're already there, you see. Which this is the same as doing it the other way around. So then you take this one and you go back one. So you add 1 to I, basically. So then it becomes IA of I2 plus 1 of x2 followed by the x1 of this one, of course. And then I think we have a rule of going from this, which is of course better matches with this, to back to this, which is then the IA of I2 plus 1 of x2 of the insert at 0 x1 xs, which is then, you know, partially solved. I think that's the base case. At least that's what we had to prove, right? Let's check. Yeah, because I1 is assumed 0, so yeah. Alright, easy. Okay. Yeah. Whoops. Induction sub. Yeah. Or induction case, I guess. Well, let's write down the induction. Nah, I'm not gonna write down the induction hypothesis. You should be able to know. Well, actually, because this is like a tutorial kind of series, let's write down the induction hypothesis. So the induction hypothesis is just this, right? It always is. So the IA of I2 plus, oh well, no, what was it again, of I1, oh then I don't need the bracket, of I1 of x1 in the IA of I2 of x2 into xs equals the IA of I2 plus 1 of x2 into the IA of I1 x1 xs. There we go. Maybe not the best way to write it down, but sure. That's the induction hypothesis. So now I'm realizing that we're running out of space already. So I'm going to have to fix that, which is image canvas size, and then we'll just no, let's go %. We'll just scale it to double the size. There we go. Oh, then we need to, of course, I should have prepared better, I guess. We need to get the fill tool, which we should make white, and then we'll fill the outside. Oh wait, layer. Oh, layer to canvas size. Layer to image size, there we go, and then fill. Oh, it's transparent. Ah, god damn it. Where is it? No, wait, opacity should be... Huh? Wait, what? Ah, here, opacity, 100%. Ah, there we go. Okay. Now we can go back to the pen, back to black. Oops. Alright. So, the induction step. So I'm thinking that they made us write this has an error, which is something we need to deal with somehow, right? Which happens only, well, wait, this is a problem because you're given that I1 is smaller than the length of XS. So the length of the empty list is 0, and whether smaller or equal, but you can still insert into the empty list. But would this be a problem then? Because if I1 is 0, well, then you insert into it anyway. If you are 0, then you insert first, and yeah, I don't think it's a problem if the empty. I don't think we need a separate case. But I seem to recall that the answer does do something like this. So I'm actually going to look at the answer right now to see why they would ever do that. Right, so you imply that I1 is bigger than 0, which is of course the induction step. I mean, that's obvious. This implies that I2 is bigger than 0, because I2 is supposed to be larger than I1. And then they say, make a special case for this, but this is illegal. You cannot assume this, because you're breaking your condition here that I1 should be smaller or equal to the length of XS, but then which is, I mean, this is 0, right? That's right. So I2 should be smaller or equal to 0, but here you say it's bigger than 0. So I don't think we need to actually do this case. I think it's redundant. So we're not going to do it actually. We're just going to assume that, which is what they will do here, that XS is just some list. But we should defend ourselves, of course. So, induction step. Let's say let I1 larger than 0. Right? This implies that I2 is larger than 0 and length of XS is larger than 0. Right? Let XS take the form of they took YS, so let's use that as well. There you go. Yeah, easy as pie. So we'll go back to what we have to prove, and then we'll copy this again, and then we'll continue our proof from there. We have IA of I1, and then we have x1 into the IA of I2 of x2 into YS. There you go. This of course equals, and then we just do this step where we take one of the head off, and then we subtract one from I2, which is then the I. Wait, why I'm not drawing anymore. What's going on? I'm drawing as the background. There we go. So that's the IA of I1 of x1 of the IA of I2 minus 1, which is allowed because we know it's bigger than 0, of x2 of, oh, I made a mistake. Oh no, oh no, oh no. Oh no. Oh no. Oh no. Can I? Yeah, there we go. So you should be like here. Then here we say what? Oh, I need to. Come on. Oh, I'm in a different. Oh, god damn it. Come on. Oh, do I have to? Oh, what am I doing? I'm using this. I should have used like penta or something. Of y followed by. Oh no, now it's a separate layer. Of this followed by ys. God damn it, Erin. Yeah. That was, of course, that was this rule, right? We just replaced it by the other side. Okay. And now we have something that looks surprisingly a lot like the induction hypothesis, which said, well, not quite. I think we should move I a bit more out still. Right, shouldn't we? I think we might want to do that, yeah. I was looking at this, right. Moving it out one, which is just applying this rule again, of course, which is then just y followed by the IA of I1, x1, followed by the IA of I2 minus 1. Oh, this, shite. This is also minus 1. Sorry. Of x2 of ys. Okay, that's it. Well, I should bracket there. Okay, and now we have something that we can use for the induction hypothesis. Where we say that we replace like everything there with the induction hypothesis. Which takes this form. So this will become I minus 1. And then here it would also become I minus 1. And this is nice because this would become I2 just normally. This is I2 minus 1, so this is I2 minus 1 plus 1. Okay, we can do this, of course, because we already assume that I1 is like above 0. It's higher than 0, it's not like... Yeah, okay. So this is IA... Oh, yeah. This is the right side of the induction hypothesis. So this is IA of I2 plus 1. Okay. IA of I2 plus 1, which is of course minus 1, so I'm just going to put I2 there. I2 of x2 into... And then it's just, yeah, just the normal one, which is the IA of I1, but this is still minus 1 of x1 into ys. Okay. Yeah, where did we have to... let me think a bit. So we had to prove... I'm trying to think of where we were going again. Well, alright, here. We're going to x1 plus 1. And then this xx should be ys, right? But that's great, because we can actually move it out now, and then it will all work again. So what we did here is move the I out, right? So first it was here, then it was here, and then it was here. So now we just move it back in. So let's look at which step that would be, or which side that would be this, but in reverse. So we can take from the left and we go right, which means this becomes IA of I2 plus 1 of x2 followed by, and then here it just says y followed by the IA of I1, that's a 1 for whatever it means, x2, x1 ys. Okay, and then we just do the same step again, so we get IA of I2 plus 1 of x2 into the IA of I1 plus, oh, this should be a negative minus. So this should be just becomes I So it's I2, but because we're taking this step backwards, it's I minus 1 right now, so it becomes just I, which is just I. Oh, then I don't need the bracket either, the parentheses. There's just I. It is a 1 though, of x1 into y, s. And yeah, that's QED. Okay, is there anything, let me go over the proof once more and explain what I did everywhere, and let's name the rules. So we have this rules, rule 1, this is rule 2, and this is rule 3. Okay, so first we assumed, of course, that we said I1 is 0, which is the base case. Then we used rule number 1, which goes here. Then we used rule number 2, but we used it backwards. Then from here we went to here by using rule 1 again, but backwards as well. And then we got here, which was our induction, or our base step. Then we wrote down the induction hypothesis, which is of course just what you want to prove. Then we assumed this. Then we didn't assume the same thing they did in the solutions, because we realized that the length of xs had to be larger than 0 anyway, because that's something you assert in the beginning. Then we increased the list by 1, which is, you know, that is, you're allowed to do that because we know that the length of xs is larger than 0, so we can just take the head. That's perfectly fine. We know that's allowed, so that's why we did that. Then here we did rule number 3, but we did it backwards. So the oh no, we did it forwards. So the I was moved from here here. Then we did that again, but this time for this section. Then we applied the induction hypothesis to get here, this section. Then what we did is we did rule 1, but backwards this time, meaning to get I back into there, which is what we did here, so it ended up there. And then we did it again to make it end up back here, which was exactly what we were going to prove. And then, I mean, if you have time left, just write like blah 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 base step plus induction step, you know, the bullshit that you always have to write down, and then you can write your square. Yeah, so we didn't do this, of course. Let's see if they do the same. They use rule 1 to take it out. Yep. Then they use rule 1 again to take it out, and they use the induction hypothesis, and then they put it back twice. Perfect, the same. And that was the last exercise. Good luck on your exam.